me to introduce the last speaker of this session, Agnieszka Kałamajska, and she will also talk about nonlinear variance or multiplicative inequalities, which are the
Thank you very much for the introduction, and also for the analysis for possibility to have this talk here. And let me start from some stories. Perhaps I'm here, the person who knows Piotr longest time, because I started to be a student with him on the same year. Let it be our secret when it was. It was after we finished the lyceum. Then, how to say about this? It was a super nice time. First of all, as about Piotr. No one knew on which year, in fact, he is. I'm saying he was on the same year as me. But my colleagues, friends who were 1 year higher on the education, they said he is from their year. And those who are 2 years higher, they also said he is from their year. Why? Because Piotr took it individually, and being on the first year, he took also more advanced courses, not only for the first year student. And I think that for first year student analysis, we just sketched. It didn't need to. So that is the story. And then, thanks to Piotr, I became interested in this area of mathematics. When at about end of my master's education, I was looking for my place. He said, why will you not join us in the research group of Professor Hajłasz? So this is what I owe to Piotr. That time, so that was on studies we were together, but Piotr was with everybody a few years or so earlier. And then on the doctoral studies, we had a seminars together, and then Piotr was a very good friend, very good, very helpful. For introducing me to his analysis. He did it with extreme enthusiasm. And there was a very nice atmosphere there. And I would like to say also, he was inviting to his flat, playing piano, was making parties, cookings, and so on. So perhaps even I would say he was 10 times better cook than me. And maybe you know it. And it's my pleasure to say, I'm meeting Piotr from time to time. He's in Poland. Nothing changed. It is extremely funny around him, and we all know that. So Piotr didn't change. The time has passed, perhaps, but the fact that this did not change. And maybe let me secure some of the photos. So this is from the 70th year celebration of Professor Będlewo, our supervisor, so you see Piotr, and then please tell me, it's a quiz, who is who? And so then let me show. So first, who is that guy? It is here. And then there is Tadeusz Zaniec, Rosario Miciona, Professor Bojarski, and Professor Hajłasz is with us here now. Oh, yes, here. It's very pleasant. So we have that box. And then also, there is also another one. Also, there's one here. So, who is who? There is one here. Then there is Mariusz Mitrei. And here's his wife, Dorina Mitrei. Then there is Grzegorz Łysik, our friend from Warsaw. And there is Piotr. So this is from long time ago, 70 years celebration of Professor Będlewo, so 2006. Then I have something nice. You say who is whom there, and the wish is who is that lady? Let us start. Who knows? Piotr, you say. This is
PhD in mathematics.
Yeah, Natalia Hajłasz, his daughter. And then there is
Ella.
Yeah, there is my daughter Ella, and part of me here. When being in Tatra, I forgot it was something like, we were after PhD, something like something. Forgot.
This in Zakopane?
It was, yeah, I think that you were also on that one, but I didn't have all photos. I just had them somewhere and forgot. So you see Natalia also, Piotr, me, Ella, and our friend Ania Ochal from Krakow, Wojciech Zajączkowski, and Frank Edwin, a young German mathematician. And that was the place. So that's Tatra. It's a very nice place. And now let me come to the story, the mathematical story. I will be talking about various kinds of special kinds of multiplicative inequalities, which are kind of my mathematical hobby. I sometimes do them, sometimes break for something else, but it is kind of related to what I did during my PhD, because I was always interested in the variable and the multiplicative inequalities, and then it started, people were asking questions, and then I was trying to do something, and then it is, in a sense, it is still in the progress. So there were many cooperators because so then I started with, I will tell later, there's Kasia Pietrowska-Pawła, she's a friend of mine, who is probability expert. Then there were three people, and there is Kasia there, who were writing masters when there were young people coming to me. Why not to give them a problem, which is not too long, but sufficient to get them interested. And it is nice thing they stayed with analysis, maybe not directly with me, but somehow almost all. Tomasz didn't finish the PhD, but they are with mathematics, and it's nice pleasure that I didn't suppose discourage them. And then there was major mathematicians, Alberto Fiorenza, Klaudia Capone, Tomasz Ruskowiec, Dajmi Pesha from Czech Republic, and recently also Artur Rutkowski from Wrocław. And what is that? What is that about? So we are interested in this kind of inequalities, and the representative one is like that. So I think let F be sufficiently regular, and then I take prime raised to the power p. Then I have h of f of x, so composition, and I can say that it is not larger than. There is like h f of x dx, and I see h f of x dx here. But in place of a prime, which is raised to the power p power is here, but I have a geometric mean volume of the function f b's, second derivative, and a certain composition of f, which I call th of f. And then there are several generalizations. We can put elliptic operator, it can be on Rn, on omega subset, which is a subset of Rn. P can be either, it is second order elliptic operator or system, something. We do something in this direction, and then look what does follow. At the beginning, I just like the inequalities, didn't ask another questions like how to apply it. We are all of that, I like, all us are like that. We like the problem, and then we think how to apply. So the whole things will become. And I was calling them strongly nonlinear, but I think it's a little bit stupid because there's so many things which are strongly nonlinear, multiplicative inequalities could be, but then at the beginning, the short is not. Then some assumptions, maybe I will skip the precise formula, but on which set they hold. For example, they hold on C0 infinity on the interval. The integrals all are over interval, but the interval can be all R. This is, for now, it's in n dimension. Then we have to, since we have FBs, we assume that F is second order differentiable, so that would be one look. And non-negative because of technical assumptions, but something can be done also. And then there's H, that H is continuous. And then what is important, that transform of F, which we did see here, that transform of F, which we did see here, is 1 over logarithmic derivative of H. So then I put f of x here. And then I have this h, which was a nonlinear way, once again. So I have h here. I have th here, but then capital H is the primitive, is antiderivative, and it can happen that we also will have the second order antiderivative. Why? So this th is simple to compute, but what follows? If we take lambda to the power alpha, when alpha is not -1, then that manipulation of lambda, the th function, is up to the constant just lambda. So what then we see in the inequalities? In the inequalities, what then? You see the geometric mean value of f and second order derivative of f. So it somehow has its kind of beauty that can disappear for regular h. And for even one can have another h which is not h like alpha power, and you can still see f. And otherwise you see something else, but you can compute this. Then the motivations one can then work, and it appears that it is nice to have such inequalities because you can use them for information, this a priori estimate or existence of PDEs in this form or PDEs in this form, where G is in LP form. So just think about it in this way. Suppose that tau just equals 1. What we have? PU equals G of x. If G of x, if P is good elliptic operator, so uniformly, we have uniform ellipticity, saying you that then, remember, we take tau equal to 1 here, then U is in W3. So we have elliptic regularity theory. How could it be powerful, somehow helpful, for understanding the disturbed elliptic regularity? Say, let me tau elliptic regularity theory. We could do something similar, parallel, to understand the tau elliptic regularity theory. It could be helpful. This is very starting, as you will see. Many things could be done here because there are many open questions. And then this perhaps with the usage of other inequalities still unpublished, one can do something. In whatever you touch, there are many questions you could do. Then, how it started? We had a paper with a friend of mine, Kasia Piotruska in 2006 in this form. Take a convex function which when we divide it over lambda square, it is bounded here 0. So it's a little bit more regular than any convex function. Then we have such an inequality. Inside you have a u composed with the Hessian second grid of u. And the square, so also geometric mean value. So there was such inequality. And it is in Rn for compactly supported function. Then let me summarize, let me say what was happening in the dimension analysis for dimension 1. Then it's a little bit easier. Easier to ask questions and to solve them, so there are more results. In 2012, Jan Peszek, who is now around his habilitation, but it was his master, we have obtained such an inequality, which was at the beginning. All the time we assume that f is either positive, and in some cases I can say non-negative, but then there are some technicalities to get rid of that and perhaps some other assumptions. So under certain assumptions, say, okay, for non-negative function vanishing on the boundary, we have such an inequality. Then, how to illustrate this? So, if we take such a nonlinearity, h of lambda, and then there are some assumptions which don't allow theta equal to b1 over b prime. will be visible here, is larger or equal to, also I mean, I'm not saying there is no results, I will later come back to that, but they are, I mean, we did what we could, but something we're passing to another questions, I mean, there are many things which could be done here. And then what appears, we have such inequalities. There is theta, and there is theta, there is p power, there is certain constant, I think it is precise, something from seminar, but PhD students showed me that it looks that it is, by validating some asymptotic, that this is precise constant, and then we have such an inequality. From the beginning, just the symbols, we just look at it, and what happens? Take theta equal to 1/2. And then it appears, you can find such a statement in the book by Mazias of all spaces as a lemma. I will tell you about it and why it was Mazias so interested in that form. And I would say, me myself, I didn't see in other places such inequalities. Perhaps one can say perhaps people were not motivated to ask about that inequalities because usually you don't do everything but something which relates to something. Then maybe I will give a hint how to prove this. I will give a hint and then many of you will be able to provide, all of you. Take just that simple case of p equal to 2 and h is constant. What I do is u prime times u prime, so I switch and I have u prime. And what is that? I have a square. I take a square of root of u prime and raise it to power 2, so it's okay. Now, if I don't have 2 times 1, then 2 times p, I can write it in this way because it's the same. And then raise that derivative on the left-hand side, once I can do that. And then there are 2 derivatives. When I compute, it is that number times u prime raised to 2p minus 2 ub's times u. But then I use header, and then what I see, what is there here, you can see it. It is the same as on the left-hand side, but there is power. So if p is larger than 1, I can divide by this, and I get what I wanted. Then if this is u prime to the power p times some h of u, I do more or less the same, but I take capital H, so antiprimitive of u, type of u prime, so there will be u prime times h of u. That's the difference. There will be u prime times h of u. And then I repeat the computation, use further, and so on. That's the idea, how to get this. So you see, it's very simple. Then I'll ask another questions. Could we generalize it to some Ornish setting? So there was p power, and what in place of the p power? So this we did with Janek Peszet. So let n be a convex function which satisfies such estimates, so it implies delta two conditions. And then there is this small h functions, which is somehow regular. Because if I take h prime and multiply it by capital A, the modulus is estimated to h raised to the power 2, which means it is quite regular function, not nonlinearity, which can be admitted. I don't know how about other nonlinearities, what can be done. So if h is sufficiently small and we add some other assumptions, then we get such an inequality. So h is in place inside the bracket. So m is convex function, f prime times h of f dx. So it's not outside, it is inside. And when the p power doesn't matter, but if we convex function, it is important. It's not larger than. We have the square root of the same as in the case of p power, and we have the same nonlinearity, but inside the bracket. So it means it is a generalization. First we had the p power, but we had in some in some reasonably regular classes of convex functions, we can have also such inequality. Then, so the application, let me look at something when there is inequality, but how it will be applied. Then, let me emphasize that we have seen that proof in the book by Mazia, Sobolev space. There it was a lemma on the series. And then could we use that inequality also on the service? So doing something with this, what appears? How Mazia used that inequality? He did to study the embeddings of, in this way, the u raised to the power p in Ln space, which is Orlich space. I would skip the whole definition, but say Orlich space is not larger than u independent constant times second grid of u raised to the power p in Lp. This is how Mazia used that inequality. He did study the embeddings. And we have used that statement to study the embeddings in this way. In place of p power, put m of u where m is convex function. Then we get that, let us remember, this is inequality 6 for a non-negative function, which is kind of a problem, perhaps, but it was also the embeddings, it was in this context. And so we have used that statement to study that embeddings, that it is kind of second order Poincare inequalities because we have u, m of u, we have then. So we had such a statement, which says that under certain assumptions I would prefer to skip that inequality. So Poincare inequality is equivalent to the isoperimetric inequality, which is that one. So the mu of A, the set, Legendre transform inverse of 1 over mu of A is not larger than constant times the capacity of A, but second order capacity with respect to n. Second order capacity is this one. This is infimum of the integrals of m of, so modulars, m of second grid of u, where u is in zero infinity, there should be something. U is larger than 0 in larger than 0 in omega, but it is 1 in the neighborhood. So this is the usage of this inequality. First, you see the nonlinear inequality. You see first, you see u and u b's, say, or but at the end you apply Poincare inequality only between u and second derivative of u. So what we needed, in fact, is when inside M it was modification of this Mazia's method shown here. Now, so this is one aspect, capacity. Then another aspect is, I mentioned, we could use study PDEs, nonlinear variants, and think about kind of a tau elliptic regularity theory. Elliptic in n dimension for now, so far, but say kind of n tau elliptic regularity. And these are, think if f vanishes on the boundary, it is okay. I would say, think about it in this way, and we do not go to the boundary. So there is tau, and tau is this nonlinearity, tau f, and f to have second derivative, it must be Sobolev class locally, the second order, and then g, let it be in LQ class, like if tau equals 0, it will be regularity with function in LQ. Then q is here, it can be 1, but somehow I wanted to link it with the elliptic regularity. And then the R is okay, I would say certain set, it is described as boundary condition, and it is okay with the boundary for the division boundary condition. Then The question is the following: how to approach that problem? It's very, very simple as an idea. So I started with that equality, and just it shows me that, look at it. It shows me that if I divide it by tau and take the modulus, I see such inequality, such an equation. Then find a nonlinearity h, find function h, such that you can write this quantity in this form. The h of f, raised to the power q, and this is what I have here, so it can be ignored, times h of f of x. So what is unknown? I know tau. Knowing tau, give the h. How it looks. How to approach this? F prime is in the same power here, and a second, and this is the same power here and the same power here. So just ignore it. And what we want to solve? We want to find such an h that 1 over tau modulus raised to the power q equals to modulus of capital H over small h, so 1 over logarithmic derivative raised to the power q times h. So we have to, what is known, what is unknown. This is known, capital H and small h are unknown, so this is only E. And then you can solve it. In many cases, you can do it not in very difficult way, and you can even go up to the time because there is a module. So in many cases, you can do that. I don't know how advanced, what are the difficulties if you have just say if the engineer tells you some h, but in some cases it's very simple. And then let me continue this slide. So we applied it in this way. We have that inequality where zero boundary conditions or kind of Dirichlet boundary conditions sufficient that for the solution we have this inequality. And then what is that? What is that? That is precisely g raised to the power q. So it is what we see here. This is right-hand side in the inequality, and this is what we see here. That g. So this is g raised to the power q. G is known. So when we know that this is finite by assumption, which means that this guy here, f prime to the power qq times h of f is integrate. But there, how to interpret this? This is 2q power certain of the derivative of certain composition of f. And it's very easy to find what composition. So how to do that? We have that inequality. That left-hand side is not larger than g in the power q. And then it means that this is in the form, what we see here is in the form g of f prime raised to the power q. It is precisely what we see here for such g. Then it means that the g of f is in that one, because once this is on the interval by one carrying inequality, means that the derivative of g of f raised to some power is integrated. So it means that also g of f. So g of f is in W1 to 2 or bounded interval. I'm just showing the example. So it means that if g of f is in that class, it inherits all the properties which we know for that class, W1 to Q. So it means that you have kind of a Herder continuity, Sobolev inequality, regularity, asymptotic behavior, all the stuff which is known for Sobolev spaces, but not for the function, but for the composition. And we precisely know what the composition to use. So with Kasia, is Kasia here? Maybe not, because she has a small child. So Kasia was semester. We also did, so that with Jan Peszek and Kasia, we have obtained some generalizations. So F can be non-negative, not only strictly positive. And then there were some further examples which I mostly skip, but I showed the statement, the example statement with Jan Peszek. So since all the stuff is for composition, so we have this a priori estimate, we have Herder continuity. But for compositions, And in case of the nonlinearity, like which was before, h to the lambda to the power alpha. And then we also have the asymptotic behavior near the endpoint 0. And so we can do that stuff, we know something about the a priori estimates. And then some remarks about this. So we got that in that case of nonlinearity, which is in power form, we have the certain composition of f is in W1 to Q. But in the elliptic regularities theory, the function solving was in W2 something. So could 1 be substituted by 2? So we had also, I mentioned as extension with Kasia Nazowiecka, it was her master. And then the questions is what I mentioned. We have that the composition here, the composition is in W1 to Q. Could we have that composition in W2 to Q? W2Q? No, it is not. There is a counterexample. So we cannot have that well as in the elliptic regularity theory. When trying to ask that question, so let me call it tau elliptic regularity. Then, so maybe not the 2Q, but maybe some SQ with some smaller s. So maybe one could have some kind of non-integer symbolic spaces. But I have no idea, no one tried, this is just a question. So I don't know what is the solution, but I think it would be interesting to know what is the link of tau elliptic regularity in that setting. Now, what do we have better? Here there was a geometric mean value for some inequalities, and it was assumed that P is larger than 2, larger equal to. If P is smaller, can we have something else? So with Claudia Capone and Alberto Fiorenza, in 2017 we had such inequality. And what is here, on the left-hand side, there's no this weight h of f, but we have a convex function. On the right-hand side, we have the convex function that here, when p is different than 2, when p is not different than 2, then it is the same, just geometric mean value. But when p is smaller than 2, we have the pth power of f prime times certain transform of f, but that transform stops to be, is now, that depends on, it's not non-local form, it is integral form. And then if I take p equal to 2, so this is psi p of s, they call it sometimes French power, I don't know, but this is my friends from Brunswick call it French power. So if I put here and integrate, this is this transform and divide it over f over p to the power minus 1. But if equals to 2, that what I see tau 2 is the same. It is 1/2 of f. So it means that we had a square root of f prime, f b's 1 and constant time f, which would be the same as with Kasia Biedruska I was showing at the beginning in n dimensions. But then there was the assumption that time that he's that there was equal to p is what is p. P was 2, so there was the same function. But I would like to say there are two. How to have that inequalities, we need to know something in indices. So this is Simonenko index. It must be larger than 1. And here is Borg index, which should be between 1 and another. And let me just quickly show that indexes, they are here. And we have them here, Borg indices and Simonenko indices. There are such numbers related to the convex function. So they are related to the how regular, in a sense, are those convex functions, and this is how much I know about this concept. Approach, we had some inequalities with maximal, how did it with maximal function there, but I skip it. And then, so that was about n larger than 1. What is in higher dimensions? Then we have something. Then, when I was talking about that, as you see, it lasts some years. When I was talking about that, there was, some friend of mine has asked me, what if you have the elliptic operator on the right-hand side, an n-dimensional thing? So just think about, instead of second derivative on the right-hand side, put the elliptic operator there. And then look what will, can you have it? So I asked the question the following. Can we have uncertain class of functions inequality like that, where there is operator, there is an operator P, but what can we have here? So not FBs, what is the substitute of the second derivative of f? So for the beginning, if we just take the elliptic system, second order elliptic system, not operator but system, then we had it with Tomasz Koczewski, and also for the Laplacian, we had it with Tomasz Koczewski, so he was a master student. And then if we take P equal to 2 and uniformly elliptic operator, but more interesting for us was more difficult case was expressed in the non-divergent form. Then we had it with Tomasz Roskowiec and Vladimir Pesha recently. But P equal to 2 and the other things are in the notes, but I can say you can get it, but the questions are many questions, because then what the assumptions, whether they could be relaxed, there could be many things, many questions asked. And so why should we be interested in that setting? So there are many equations like that which require kind of regularity. The Keller-Osserman equation, then Ender-Fowler problem, including dynamics, you see it this way. And then in electromechanical system MEMS, one can see such a equality with the Laplacian, and Liouville equation is in this form, but perhaps we could be disturbed with the equation in this form. So you can see there are some motivations. And then I was, a friend of mine was asked this question. She's Patrizia Donato, and she's partially in applications. So that's why she asked that question quite a long time ago even, and it lasts. So now we think, let me say about this situation in case of the operator P, which is second order elliptic. So we have U in second, locally in smaller space, in second order smaller space, and then we can put PU. There is strong ellipticity, uniform ellipticity condition. And then the corresponding norm, of course, equivalent to the Euclidean classical norm, but we can use it in this also, this norm. And then the inequality, so this is P. Then we had, but let me come back also. I mentioned that this is the operator, and then we have the following probability. But for that, under that assumptions, we have the following identity. Why identity? For the beginning, I was thinking about inequalities, but friends of mine who are in probability doing like identities, and Krzysztof Bogdan, a friend of mine, he's a probability expert. He asked me about why not to think about identity. So why not? So we have the identity, and then it looks in this way. This is small h, this is capital H, which means that h, so h prime is equal to small h, so it's antiderivative. So we have such a identity under such assumption. There's the divergence of A. A was a matrix, so divergence is you take the divergence of every row, then you have a vector, and that vector is scalary multiplied by grid of u, and then you have this capital H also, so antiderivative of u plus theta, and that theta is interesting since we assume that h tilde of u, I omitted the assumptions, is locally, is in w tau 2, 1 of omega. We assume this. So the gradient of that is in w11, which means that it is integrated over the boundary of omega by the trace theorem. And we have such an expression. So this is normal vector transpose times matrix times the grid of second order antiderivative of u and integrated over the boundary of omega. Of course, omega is regular enough to have that. There's no questions about pathology, but just to have some information about it. Then we also know that the integrals converge, and let us think. So there is such a theta. It's kind of difficult, but sometimes we know its sign. For example, in some cases we can say this is you can say if A would be just an identity, it would be normal times the gradient. If h tilde of u is from 0 to something positive inside, then it means that it has a sign against the normal. So we have this equation that the gradient maybe is not perpendicular, but if u is growing in this side, then the normal is outside, so it means it has the theta, you have a scalar product, so this is normal vector, this is the grid of h tilde of u. Once you know that u is positive and that h tilde is positive, it means you can know what is the sign. So finally you have the inequality, where this boundary term can be omitted. But still we're puzzled with this. And also in that statement there was an inequality, which is simply you just had the identities of the inequality, but there was something had to be done here, perhaps even not with the best constant. So we have something like, let me say, kind of, it's not Poincare inequality. You have Pu and this antiderivative of small h of u, but you have another function which depends only on u without derivative, and you have that boundary term. And then you can have inequalities. Having that, so just let us remember that there are such inequalities which hold. Now, there is an aspect which is related to probability, namely probability potential theory. In 1931, Hajłasz had the following formula. Once you have a harmonic function defined on the board, then we have such an identity. The grid of u raised to the power 2, when integrated, it is the same as double integrate of what you see here, g of eta minus g of psi raised to the power 2, and the sinus square, so it's like almost psi minus eta over 2, the eta d psi. And then what is g? So u was harmonic, but on the boundary it was equal to g. Then there were many applications of that formula. So there are the names of people. So it was related to the Markov processes and Dirichlet forms. there was started in 1931, but you see, for example, there's papers from 2012. Then you can find also in the information in the book by Azit about generators of analysis of sine groups. And then also in harmonic analysis starting, so I give some data, as you see, there are also recent papers. So that information I got from friends probably who are probability experts. Then, so in the paper from 23, there was a paper by Krzysztof Bogdan, Fafuła and Artur Gutkowski. There was a precise formula for function defined on omega related to that Lewis formula. Here, it's not precisely what is that in that formula, but let me call it I. So I take the group u raised to the power p2 times u to the power p minus 2. So it is like in our inequality with non-linearity h equals to h of lambda equal lambda to the power p minus 2. Then there is such a formula, and you see there is a double integral, similarly like as in the Davis formula, but now we don't assume that u is harmonic, so this is just a Laplacian of u. What is g? It is harmonic extension of u outside the domain. So there are some explanations. So this is this g, this is Poisson integral, so extension of v where you have a condition on the value reconstruct the harmonic function, which is that v on the boundary. So how to link it with our result? So we use this our identity, which we had, I recall it, with kind of non-linearity. And then what appears? Let me recall, theta is then of that form. I use it, this is the same I, with the I is here, and I have the I here, the same, it is the same. So I use these two formulas, and what we get the following formula. We get theta also in our expression. And then when using those two formulas, we get the representation on theta. Theta is in this form. Double integral, yes. Then something with the Laplacian of u, harmonic extension of the boundary. And then there's recalling that what is g raised to the power p minus 1. This is French power, this modulus of z p minus 2 times z. So it's like z to the power p minus 1 for positive and minus the modulus z to p minus 1 for negative. And then one can ask many questions related to that, because we had some special assumptions, and then there's how it works. In many cases, more or less, most of the questions you ask, I can say I don't know why, but maybe some people would be interested. There's a lot of young people, so maybe you find it interesting. So I don't know many answers on are unknown, and also how to link this theta, which we had given by one integral, so this one boundary integral, how to get the representations in general for the two integrals, boundary integrals. And then also some other things. So again, let us consider come to the problem which we did solve with Daniel Pesha and Artur Gutkowski. It's very recent. So now let us think about the equality like that. It was F piece before, now it is an elliptic operator, and that more interesting case is so kind of technically more difficult, non-divergent one. And then what about that equation? How to interpret this? Let it be, I will say it soon. So what are the assumptions? Let L be in L1 and F is non-negative. Let it be sufficiently regular domain. And then consider that equation, but not precisely P as that one. It requires too much of the assumptions. But first I define that operator, then switch some of the derivatives, and somehow extend. Let me skip this, but if you ask, I can show. So it means first we have it in a good class, but then we can extend it in that way that have evaluated on C0 infinity, for example, put and switch the derivatives on that phi, that trans function phi. So then you can extend in various ways. Either you can skip one derivative on U, or you can skip two derivatives on U under some good assumptions on that matrix that it is, for example, C2. But what we also assume, let U be strictly positive and L1 of omega, L1. And then we read this. I say it is certain as some extension of operator, so U insert itself does not need to be that regular to have this formula, but somehow we extend. Then U is only in L1. And then how does this boundary data 0 reads? It's this way. I take the omega epsilon is where the distance is smaller from the boundary, is smaller than epsilon, then integrate it over the omega epsilon, so that strip near the boundary of omega, divide it over epsilon, which means more or less that I divide it by the volume of this omega epsilon, and that should go to 0. So this is very weak understanding of the trace. We are not using trace theory, we just use this. Now, we have the statement, so existence. I was saying we can use it to the a priori estimates, but all of us has finished, or most of us, the course on PDEs, which says once you have a priori estimates, Schauder type fixed point theories give you existence once we know how to approach it. So it is in this style, we have the existence theory, there are certain things about regularity, and let me skip precisely, but we say depending on the gamma in the PDE, the power of U, we have various kinds of regularities, and then always in all that situation, U raised to that power is in some space W12, so this is H10 with 0 boundary condition, and we always can know that right side of this PDE here is integrable. We always get that by the existence, and we also can say that U, the solution, behaves like is bounded from below, like by the distance from the boundary. So we have certain kind of also asymptotic behavior near the boundary. So this is existence regularity, let me call it. But then a lot of you would ask, well, what about uniqueness? Let me also make a comment. So if P was in divergent form, we had the non-divergent form, then there was a result by Bocardo and Dorsina quite of interest. There were many quotations of that paper from 2010, so a long time ago, and then we couldn't find any results with P which would be non-divergent. We used that multiplicative inequalities which I mentioned were basic of my talk. So otherwise I don't know. And then the question, uniqueness of the distributional solutions, so whatever it means, it is the weakest possible form of asking. It was unknown also in that setting. And finally we found that there is uniqueness of solutions once we assume that U is in one plus, so in that non-divergent form. As far as I know, also for that non-divergent uniqueness in distributional setting, we did not find it. So here's the literature. That's quite a sequence of papers because, as I noted, there were some many operators who were very helpful. helping with this. That last result is still on arxiv only. That's about uniqueness and existence. And happy birthday, Piotr.
Okay, thank you for a very interesting lecture. Are there any questions or comments?
So I was wondering, are there some cases when you get the optimal constant in this inequalities? Or?
Only in one dimension. There was, but I have no proof, but there was some PhD student coming in probability, and he showed me that if looks at asymptotics, he had some kind of example that the constant in that inequality is 1D with the p power, and some non-linearity like h of lambda equals lambda to the alpha is probably sharp, but there's no published result in this direction. One should. It was not long. It was not a long argument. It's like more or less in the style like people show that hard inequality is achieved with best constant, and to do that, they don't have a precise statement but asymptotic behavior. By asymptotic analysis, they show that this constant is precise, and probably he was kind of motivated by analysis of constant for the hard inequality. It is in this type, but only there.
Any further questions or comments?
So you said you don't need, I mean, the regularity of the boundary is not a question you're assuming, but what is kind of the minimum? I guess you need a normal, some notion of normal.
Yes.
That's it, I guess.
Let me say, maybe we did some with C2 boundary.
C2.
Maybe because it was not main question, but just we were assuming what can be assumed to have the result. So in a sense, I don't remember precise, but it was not just for any domain.
Okay, any further questions or comments? No, then let's thank Agnieszka.
What is